तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we continue the discussion on concepts of illumination and shading in the course on computer graphics. In the last lecture, we introduced the concept of illumination and shading from the point of view of the last stage of a 3D graphics pipeline, where we have a set of polygons, and those from this set of polygons we have removed some of those faces using backface culling, and we have found out the visible surfaces or parts of some visible surfaces using any suitable VSD algorithm. You can visualize either ray tracing or Z buffer algorithm. And we spent a lot of time discussing why the process of illumination and shading of a polygon or any point of a polygon or a point x y on the image plane or a pixel is a hard problem. So, we will start from there, where we assume that a lot of compromises and simplifications are considered in order to solve the complex problem of illumination and shading, which is a big burden or a bottleneck in terms of trying to create pictures which are appearing as real as possible, because we are trying to create reality, virtual reality and visual realism to create realistic effects in scenes, and illumination and shading is an important property of that. So, the complexity of the process of illumination and shading comes from the fact that you have one or more light sources and several sets of polygons in a complex scenario. I talked about a million, but in certain cases, in very greater applications, you may have several orders of tens of millions of hundreds of millions of polygons for that matter in a very complex scene. So, you can visualize how complex the scenario can become, not in computational complexity in terms of generating the scene, illuminating the scene, but also in trying to find out the exact illumination which would be proper. So, the typical compromises and simplifications which are done, as seen in this slide, we have talked of this in the last class, is that we assume a uniform media, we assume opaque objects, we assume no interreflections, or even if it is there, it is approximated by what we call as ambient light, point light sources is what we assume, and a very simple color model. Out of these constraints, simplifications which we consider, the two most important facts are the no reflections, interreflections part, where we assume that there is an ambient light present in an environment. It could be an outdoor scenario or an indoor environment, could be a classroom, and a typical example of the walls and the ceiling and certain parts of the floor receive ambient illumination, which are due to a combined or integrated or a summing effect of all different interreflected rays reflected by different objects from one to another and so on, and they dissipate in the open space. Those parts which only receive ambient light may not receive the direct source of the light rays from the source directly. Okay? If the rays fall directly from the source onto the object and get reflected to the sensor or the projection plane or view plane, then of course, the ambient term could be neglected. But however, in certain cases of background objects, okay, or background scenes, it is possible that you do not have the sources of light hitting onto certain objects directly, and it is on the ambient light which only falls on the object. Okay. And if you paint those objects which are receiving ambient light by a completely dark pixel, assuming it to be 0, the scene becomes very unrealistic. Okay. In fact, in a dark room or a darkish room, you can almost visualize that you will be able to see objects, although there is no direct light source. So, ambient light plays a very important role, and you have to provide this ambient term in the illumination component of the model which we are assuming. The second part, one of the other important part is the opacity of the objects. Opaque objects makes it much simpler, because if objects are not opaque, they are transparent like a glass or translucent type of object structures. If you have where the material property is such that it allows some part of the light to pass through the object and some part it gets reflected. So, you have to model that property of how much fraction of the light gets traversed through it, gets reflected from the surface, and then more than that you have to find out what are the light rays which are passing through the object and coming out of the surface. So, there are 3 factors which increase the computational complexity and the complexity of the modeling also when we do not assume opaque objects. Okay. But typically most objects which we see except glass are opaque objects in an environment, but of course, there are some objects which are transparent or semi-transparent or translucent for that matter, and if you need to model them, you have to have sophisticated mechanisms by which you can handle these scenarios. So, coming back to the slide here, if you look, the illumination consists of 3 parts. We talked about this in the last class, where we talk of an ambient term, a specular term, and a diffuse term. These are the 3 components of the illumination effect, and we have discussed very briefly. You have just introduced the ambient term at the end of the last class. We will talk about that in detail now today, where the ambient light is considered in the case of a diffuse non-directional source of light. It is a case of a diffuse, that means equal in all directions. That is the meaning of this term. We will talk about this diffuse reflection also and diffuse light sources later on, but in the ambient light is considered to be a case of diffuse non-directional source of light, and this results from the effect of multiple reflections of light from many surfaces present in the environment. So, that is the key. So, all these multiple reflections or interreflections from one object, which we talked about in the last class, a light source from the light source, the rays directly falling on the object get reflected in one direction, hits another object, that gets reflected in some other direction, hits a third object, and so on. This can go on in an environment. Okay. And if you have a set of a large number of polygons, not even 10 or 100, I am always asking you to visualize millions of polygons, so you can visualize how many such rays which exist from direct sources, direct rays from the source itself, and indirectly reflected from several objects, and of course, as they travel, their intensity keeps on reducing. We will see a functional model of that also, but we know the hardness of the problem here. The hardness of the problem is simplified to almost a very large extent. In fact, the main hardness of the problem is due to the interreflections of the object, which result in ambient illumination, and this component is has to be modeled in a very simplistic manner, such that the complexity of the illumination process is not very large and definitely not hard, that which cannot be solved. It cannot be solved, so we do not try to solve that problem. We assume that there is an ambient illumination present in an environment, and that is what we move on, and it results from the effect of what was read, multiple reflections of light from many surfaces present in the environment. So, if you look back, this is what I said just now, that this case of ambient light is a case of a diffuse non-directional source of light, and it results from the effect of multiple reflections of light from many surfaces present in the environment. Ambient light is assumed to impinge equally on all surfaces from all directions. This may not be also actually true. This may not be actually true in a realistic scenario. There could be variations, it may not be very large. That means, one part of the, say, the background wall or the ceiling of your room may receive a larger fraction or a larger percentage of these interreflected rays, causing larger what we call as ambient illumination or larger ambience in terms of illumination and shading in this context. Okay. So, it is possible that some part of the ceiling or even the walls, if you look around in a particular room, in a classroom or in your room, where there are no light sources pointing towards these background objects like the ceiling, walls or even floor, then, but of course, floors, most part of it receive direct sources of the light. So, I will not take the example of the floor, but if you take the background wall or the ceiling of a room, and you will find that you have ambient illumination, which varies from one point to another, but typically the variation is not that large to be considered in the computational stage. So, we assume it by an average ambient illumination. That is one sort of approximation which we do for ambient light. Okay. So, it is assumed to impinge equally on all surfaces from all directions, and the illumination equation is simplified with the product of two terms. The ambient light component is a multiplication of two of these components, I A multiplied by K A, where I A is the intensity of the ambient light and is assumed to be constant for all objects. Okay, so, that is what is assumed. So, throughout the environment or the room, you have this I A which is constant. Of course, again I said it is almost close to reality, but not if you have some idea about which parts of the scene may have a larger ambience or a larger ambient illumination compared to other parts, you can actually vary this I A component from one point to another in the scene if you are able to model it using a simple linear or even a nonlinear function for that matter. So, if it is possible, you can go ahead if you think that you could measure ambient illumination by some device, say typically it could be a light measuring device in a 3D scenario and want to import it into your graphical package to make the scene realistic as to what you saw. Maybe in a real environment, then you can measure ambient illumination also if possible using sensors, and then fit it using a nonlinear or linear function, and then say I A is a function of x, y, z if it is possible, and of course, x, y, z and v. Of course, if that is so, but it is typically assumed to be invariant to the viewer or light source direction. So, but it could be a function of x, y and z. So, that is what you need to find out. Otherwise, typically I A is assumed to be constant, that is the intensity of the ambient light, which is assumed to be constant for all objects. And then of course, you have the ambient reflection coefficient K A. This is equivalent to the reflectivity term rho, which we used in the last class. The rho will have different components depending upon the illumination component being talked about. Either we talked of an ambient illumination or a specular and diffuse, which will coming up in this class now after some time. And we will see that the rho is considered to be different for different types of lights, and it could be of course different for different surfaces, there is no doubt about it, but depending upon the light, that means a particular surface may reflect more of ambient light and less amount of other types of illumination, direct sources or diffused or specular type, which we will see later on, because we talked of these three components, but we are discussing ambient light. So, Ka is the ambient component of the reflection coefficient, ambient component of the reflection coefficient, which is also termed here as ambient reflection coefficient Ka, which varies in the normalized range 0 to 1, and of course, it is a property of the material. So, that is I A multiplied by Ka, which is giving your ambient light term in the illumination equation. This is a picture which talks about the different effects of ambient light on a typical surface. We assume that it is a sphere with a red color, and of course, it is a glossy or a shiny part which is reflecting. There is one light source on the top left which is illuminating all these spherical or ball type of a structure. This is courtesy this image has been obtained. You can find it very easily in a demonstration of MATLAB graphics toolboxes, and this has been imported. It is a very nice demonstration here, where you will find that there are about different balls with different types of or spheres with different type of ambient illumination, the largest being on the top right and the lowest being the left column. Okay. The left column typically has the less amount of ambient illumination. Still, you will see some variations as you keep going from top to down and left to right. As you go from left to right, the ambient illumination term on each of these rows is increasing. As you also go from top to down, you will also find that the ambient strength of the reflectivity of the surface and the light, both are actually varied from one point to another. Okay. So, ambient strength is increasing from left to right, and the ambient component of the light is increasing from top to bottom. I repeat again, as you go here, the ambient strength is increasing from left to right, but as you can see here that the more amount of ambient illumination is present towards the right than on towards the left, and if you go from bottom to top, the ambient light itself is actually increasing. So, it is a combination of two factors, something like you are playing around with these two terms IA and Ka. IA being the component of the ambient strength of light, Ka is the ambient reflection coefficient or the ambient component or part of the reflection coefficient, which is a property of the surface. So, both are varied here, and of course, I have not labeled these figures, but again you can visualize, as I keep repeating, from left to right you have the ambient strength increasing and ambient reflection coefficient increasing, and from bottom to top you have the ambient strength of the light increasing. So, these are examples by which the ambient strength of the light and the reflection coefficient could vary the way a surface could look like. You can have a different color combination also. So, that was an illustration of the ambient reflection component of the light source, and we talked about in the beginning of the slide today that there were 3 components of the light source. One was ambient, and the second one is the diffuse, and the third one is the specular. So, we will move on to the second component, assuming that the ambient term has solved a lot of problem in terms of the hardness of illumination and shading. It is a simple term which is approximated those infinite set of rays floating around in all directions, impinging on surface, getting reflected, interreflected back again, and so on and so forth, and it is assumed to be a simple constant term. So, that is what has simplified our problem to a great extent. Okay. Let us look into the second component, which is called the diffuse reflection. Okay. So, here we assume that we have a point light source whose rays emanate uniformly in all directions from a single point. So, we assume here now for the first time we are talking about light sources and rays coming out of the light source and directly hitting an object. So, we are talking about light rays coming out of a light source. We assume a point light source. You can visualize a sun in the universe as a point light source, because that is emanating light in all directions. An incandescent lamp almost also is a very crude approximation of a point light source, not typically, but never a torch, or a tube light is definitely not a very good example of a point light source. Some parts, some sections of tube lights, yes, but not on the whole. Okay. So, assume a point light source, and a point light source, the basic for a point light source, the basic assumption is that rays emanate uniformly in all directions from a single point. Okay. So, that is what. The object's brightness varies from one place to another depending on the direction of the light source and also the distance to some extent. I repeat, the object's brightness varies from one place to another depending on the direction of the light source. So, it is very important. If you remember a diagram which will come again now, we talked of a point of on the surface of an object, linear or non-linear surface, does not matter, and we have a light source direction. So, the light rays are coming from that direction source S, we have a surface normal, we have an incident angle theta, and a sort of a viewer direction V. The angle between V and N was phi. We will come back to that figure once again, but what I meant was that you have to visualize that figure in 3D, and we assume that wherever you are viewing this object, you see the same illumination in case of a diffused surface, which has the property of diffuse reflection. A diffuse surface has a property of a diffuse reflection. It has another term called the Lambertian surface also, we will see. So, the illumination, then what does the illumination depend on in the case of a diffuse surface? It depends on the angle between the n and s vector. That means, the relative positions of the surface normal and the source direction, the angle between them actually dictates what is going to be the illumination in this case. So, that is what is talked about here, when that which says that the object's brightness varies from one place to another depending on the direction of the light source and also the distance. We will model this distance factor to some extent later on. I talked about this term, that the diffuse surface is also called a Lambertian surface, which exhibits diffuse reflection, and typical examples of Lambertian surface which has or exhibits diffuse reflection are dull matte surfaces, snow, chalk, projection and movie screens, uniformly painted walls, etc. If you go to a theater to watch a movie, and you can watch the movie from any position on the at any point on the theater hall, and you will be able to almost see the similar brightness. Of course, there is an effect that the front rows are illuminated more than the rows behind. That is an effect of a distance, but that is not due to the effect of specularity or the property of Lambertian surface which we are talking. What I am taking, if you take constant radial distance and move anywhere in the theater hall or the movie hall and you are keeping watching the movie, points on the surface of that movie screen will appear same. It is typically same for projection screens also, which are used to project presentations. So, that also is supposed to illuminate or dissipate light equally in all directions. So, whatever light falls on a point, there is a little bit of granularity of that Lambertian surface, such that it dissipates light equally in all directions. That is the key, that it dissipates light equally in all directions. And other examples are chalk, snow, dull matte surfaces. Any matte surface, tabletops typically, unless it is textured, forget the texture part of it, do not worry about that for the time being. If you have a flat surface, maybe the background walls, as you can see, if you observe these background walls from any direction in your classroom, walls painted with certain diffused color, whatever could be the color, white, blue, or whatever it is, then but if it is painted with a color which has a diffuse reflection property, you should be able to see the same illumination from any direction, because the illumination component only depends between the angle between the surface normal and the light source direction, NNS, that is the key. So, that is what we saw for diffuse reflection for a Lambertian surface which exhibits diffuse reflection. So, we will keep interchanging these words Lambertian, diffuse, and interchangeably. Okay. So, when you talk of a Lambertian surface, we will understand henceforth that it exhibits diffuse reflection, and we talk of a diffuse surface or a diffuse reflection, we are talking of a Lambertian surface. So, that is what we will use interchangeably. These laws have come from concepts of optics, of basic physics. Okay. So, these surfaces, as I was talking, appear equally bright from all viewing angles, because they reflect light with equal intensity in all directions. This is what we just said now. We talked about this, that they reflect light with equal intensity in all directions. So, independent of the viewer direction, you will have, that means whatever be the viewer direction, you will have the same illumination of object points which are of Lambertian or diffuse properties, and they appear equally bright from all viewing angles. For a Lambertian surface, the amount of light seen by the viewer is independent of the viewer's direction as follows. Let us look at this figure which we bring back, as I was promising some time back that we bring back this figure, where if you remember that we are interested to calculate the diffuse intensity at an object point O, and the source at a direction S, viewer is of direction V, and N is the surface normal. And the angle between, remember this is again a 3-dimensional figure, V, N and S may not lie on a plane in general, and the angle between the vectors N and S, again repeat, N is the surface normal, source is the viewer direction, this arrow shows the direction of the light source, not the direction of the source vector from with respect to the object point O. N, of course, N and V shows the direction of the N and V vectors show the direction of the surface normal and the viewer direction respectively. To know the vector S, which points to the source direction, you must reverse this arrow, but in this case the arrow is just pointing to the light rays coming out of the source S and impinging on the object O, and the angle between N and S, which is also called the incident angle, I have put a label theta. I have purposefully omitted this angle, which was given as phi in the previous class, the angle between V and N, because it is immaterial, or it the diffuse component of illumination is invariant with respect to the viewer direction, and hence this angle. So, the illumination component which you get is going to be independent of the angle between V and N. So, that is why the term is eliminated from that figure. It will be only dependent on theta by this following relation, IS KD cosine of theta, where this is the diffuse illumination equation I was talking about, shown in the previous slide, where IS is the point's light source, intensity KD, which varies again from 0 to 1, is the material's diffuse reflection coefficient, and of course, theta varies between 0 to 90. It is a cosine of a theta. So, you can almost visualize that when theta is equal to 0, that means N and S coincide, you will have the maximum diffuse reflection, okay, or in diffuse intensity, whereas when theta is close to 90 degrees, you will have very less amount of illumination due to diffuse properties of the surface or diffuse reflection. And again the KD term, if you look back, it is same as that Ka term. In the ambient illumination term, we introduced the ambient reflection coefficient Ka in the earlier slide. In the current slide, KD is talked about the materials diffuse. The D stands for the term diffuse. So, the diffuse reflection coefficient is KD. IS is the point's light source intensity, which is a very important factor. Earlier in the ambient illumination, we talked about an IA term, which was due to the result of various light sources, light rays getting interreflected about various objects and resulting in an ambient illumination. So, it could be a combination of various rays which creates ambience, various light sources also. But here at an object point getting illuminated by one light source, we may have many, we will come to that, but one light source will illuminate one point on the object, let us say, and that particular intensity of that light source, is going to be dictate what is the intensity in terms of the diffuse reflection component of that illumination. So, IS, there is a point light source's intensity, Kd, the diffuse reflection coefficient, and a theta term. So, for the other angle phi is irrelevant. So, you can put V anywhere, as we had seen in the previous slide here, and V could be anywhere in 3D diagram here. It could be along N, it could be along S, it could be anywhere else. The diffuse reflection component I here in this equation does not change, it is invariant to this angle. So, I have not labeled this angle as well. Okay. So, this is the diffuse illumination equation which we have, IS Kd cosine of theta, and the above equation can be rewritten as the following manner. This is what is usually followed: IS Kd and a dot product of n and v vectors. Cosine of theta is can be visualized as assuming n and v to be normal unit vectors. Assuming, or if they are not even unit vectors normalized, then you better normalize them. And the dot product of two vectors, what is the formula? We had seen this many times, we have used this in backface culling as well. It is the product of the amplitude of the two vectors, it is a scalar quantity. Dot product is a projection of one vector onto the other one. A dot B, project A to B or B to A, whatever the case may be, okay. And the direction does not matter, the order does not matter in terms of the dot product, and the formula is the product of the two amplitudes of the vectors n and v and cosine of theta. And since I mentioned just now that you better take a unit vector, normalize the vector n and v, so their amplitudes will be 1. So, n dot v in this case will be cosine of theta, because the amplitudes of both n and v are unity or 1. So, that is what we are able to replace the cosine of theta term by this dot product of n dot v, assuming this to be the normalized unit vectors along the surface normal and source direction. So, unless you are in a perfect dark room, which is typically used for developing films, a more realistic illumination equation using the concepts or knowledge which we have studied so far is the total intensity I, which is the sum of two different components. The ambient component here given by IA multiplied by Ka, and the diffuse component of the illumination consisting of the IS Kd and dot product with S, where Is is the intensity of the source, Kd is the diffuse reflection coefficient, n the surface normal vector, and the S is the source direction, and IAK are also similarly the ambient illumination and the ambient reflection coefficient. So, these are the two terms which can now be combined to make the scene look realistic. In the case of surfaces having diffused reflection properties and also ambient illumination due to interreflected rays by other objects. So, we combine these two illumination equations and see the effect. Now, there is another, of course, the effect of distance which I was talking about, which talks of effect of distance or attenuation. It is possible that, as I was saying, that although when you watch a movie in a hall or a theater, you can sit anywhere in the gallery and watch the movie and see the same illumination and have the same effect as part as visibility is concerned. The illumination on the screen is same from or independent or invariant with respect to your position in the gallery. Although this is true, but I also mentioned, and you must have realized that when you are sitting on the front few rows, you definitely see a larger illumination than the people at the back or at the middle, definitely at the back of the theater towards the back. Okay. So, although seeing from the frontal few rows in movie may not be very pleasurable to the eye because of the very large illumination where the light rays will be glaringly impinging onto your eyes, could cause a very hard or a burning effect after some time. It is not advisable to do so in general because of that particular reasons due to the health of your eye, but the illumination is very large, and so it is preferred that you have a seat in the middle or towards the back of the theater. But what basically means in terms of illumination and shading as far as computer graphics is concerned, that there is an effect of distance which causes attenuation of the light source's intensity. So, when you have a light source very close to an object, if there is a light source very close to an object, you will typically have a larger amount of illumination. If you take it away, if you do take it away, the illumination starts glaringly. See, if you come forward, the illumination will be brighter, and if you take it away, the illumination may go down. Okay, so, there is an effect of distance which reduces the light source's intensity as it traverses. I was talking about this when we talked about interreflections of ambient illumination, where the light gets interreflected between various parts of the object and they have to travel. So, as they keep traveling and getting interreflected, their intensity also starts falling down in some sort of an exponential manner. Okay? And so, after some point, of course, you do not have to worry about although there are infinite rays, but beyond a certain point, since those light strength intensity of those rays will be falling down anyway. So, you do not have to worry about that the ambient term will be very large because of that. Because the ambient lights which fall on a surface would have been reflected by several hundreds or more objects. It would have travelled a lot of distance before actually coming and hitting on that surface which is exhibiting ambient illumination. Number 1, from the point of ambient illumination also it has an effect which is approximated by an IAK term. We do not worry about the effect of distance there, but it has a role to play which is approximated there. In the case of a diffuse reflection, where light sources directly come from, light rays come directly from the source and impinge on the surface without passing through or getting reflected by some other object. Okay? So, it is directly coming from the source and impinging on the object. If you take the object away from the light source, the effect will be such that the illumination will start falling down. It is typically a case that when you move closer to the sun, in terms of if you are able to move from one planet to the another, okay, from Earth you go closer to a next planet, okay, or move away to a farther planet, say Jupiter, Saturn, or even farther away, you will see that the intensity of that light source of the sun is also glaringly low. It typically happens also moon when it rotates around the sun, depending upon its distance, you will see a brighter moon or a very dull moon. So, there is an effect of distance. Of course, in the case of the atmosphere, there are atmospheric effects which often cause an effect of a dull. Of course, if the cloud cover, you may not be able to see the sun or the moon, but atmospheric effects in terms of the troposphere and the pollution in the air may cause the brightness to also vary. But since we assume smooth medium, we assume that light travels in a vacuum without any interruptions, and when you are closer to the source, you have a brighter effect of illumination as you keep dragging away, as you keep pulling out or moving away from the source, the illumination will start falling down. So, let us try to model this effect of distance or attenuation with an equation, where we change the previous equation of illumination model using an intensity I, the same ambient term. There is an f attenuation function which we put here before this term here, in terms of the try to put that term, we are putting that term in on the diffuse reflection component. Okay, the diffuse illumination part here remains unaltered, and we just add a multiplicative term f attenuation, which is a function of distance, and the two typical distance measures which are used often are these two. Okay, 1 by dl square, L being the light distance of the light source, and the object is written as a dl, and you can take 1 by dl square. So, 1 by dl square, 1 by x square function, you know, typically it will have an exponential fall, and at dl very far off, the asymptotically will go down to 0. This is the case which will happen, of course, if you are moving away from the light source in an artificial environment like, say, the incandescent lamp or tube light. Although you may be able to see the light from a very good distance, but the effect of illumination of that light source on the object can be considered almost to be negligible if the object is sufficiently far off. Okay, so, 1 by dl square, when dl is very far off, it is not a problem, and when dl is equal to 1, you will have the functional value go to the maximum. DL could be less than 1, and there is a problem if DL is very small, asymptotically approaching 0, the F attenuation term may actually shoot up to a very large value. So, this value of 1 by DL square, the functional form, has to be used with a lot of care, precautions, in the sense that what you visualize is that DL is a positive number, usually typically more than 1, that is what you assume. So, if you are certain that the value of the DL which you are using in this F attenuation term given as 1 by DL squared, if you are using this functional form and you are guaranteed, or you somehow ensure in your programming environment and you are sure in the scene which you are modeling that the value of DL will be 1 or more than 1, then you can safely use this, otherwise it is not. But in a programming environment it is difficult to guarantee such things unless precaution is taken. So, a very safe functional form is given in the next one, which is given in this form. It is more realistic, a nonlinear term in the denominator, all right, but this term takes care of the fact that this can handle even in the case when DL is equal to 0. What will happen when DL is 0? Well, it will be the minimum of this function, that is 1 by C1 and 1. Okay, so, you have two constant terms where C1 and C2, you set those terms depending upon the way you want this attenuation term, which is a function of a distance, or it is trying to capture this effect of attenuation based on the distance of the light source and the object surface. Based on the distance between the light source and the object surface, you have a the effect of attenuation. So, that is trying to be we are attempting trying to capture that effect by this functional form, and minimum of that is what you are taking. So, that means if the value of 1 by C1 and the denominator term shoots more than 1, you choose 1. If the value is less than 1, you choose that particular term. So, that is the minimum of these two values. So, if the frontal term with the help of this constant C1, C2, C3, there are three constants here, and there is the DL, which we know what is this, which is the distance of the light source and the surface of the object, which is under consideration. So, if this term is less than 1, we consider that, otherwise if this term shoots over 1, we take the value of F attenuation to be 1. When F attenuation is equal to 1, we have there is no effect of distance in that case, because it is equivalent to considering that previous equation which we talked about. So, this is the original equation which we started with, and that in that case, that is, it can be considered that this equation is a special case when the F attenuation term here is equal to 1, otherwise it will be typically considered to be less than 1. So, that is how the effect of distance is visualized. Okay. There is another concept of atmospheric attenuation, which is considered, it is similar to the effect of distance which is considered, and this is a process we will see here. It is a process of simulation of the effect of depth queuing. It is a process of simulation of the effect of depth queuing, where distant objects are rendered with lower intensity than the closer ones. So, that is a term which is also used to model the same, and using normalized projection coordinates. If you remember the 3D graphics pipeline, we used to predefine these parameters called as let us go through these parameters which are used to model this atmospheric attenuation. The first of them is the scale factor, two of them which are used, which are again varying between the range 0 to 1 normalized scale factor range. We have the range of depths now, ZT and ZB, something like a background depth and a foreground, you can say ZF and ZB. So, we assume that there is a range of depths. We also did this in the case of a canonical view volume, when we were truncating or scaling down the entire 3-dimensional rectangular parallelepiped finite view volume. For orthographic parallelepiped or a pyramidal structure, in the case of perspective projection, we also had a foreground and a background plane, if you remember when we were discussing 3D graphics viewing pipeline much earlier on, and so we have a range of depths, of course. So, that is what is considered here. ZT and ZB could be the range of depths which will dictate what is going to be my scale factors, ST and SB respectively, that also should always be in the range 0 to 1, and we have a depth Q color IDC lambda, okay, depth Q color, which is the color based on depth, original intensity of the source I lambda, original intensity of the source I lambda, and we based on these values we have to compute the depth queued value of intensity, depth queued value of intensity I lambda prime. So, we have to compute this I lambda prime based on the other factors like range of scales, range of depths, and the intensity depth q color also, which is given by IDC lambda and the original light intensity. So, let us see what is the functional form which relates this I lambda prime with the other parameters here to get our atmospheric attenuation function. Okay. This is the function which we have to consider, which is considered as an I lambda prime is defined as S naught multiplied by I lambda and this particular term. You can see that when S naught is calculated based on depth and scale. So, if we go back, you have to, this is all known to us, that means range of depth ZT and ZB are known. You set your STSB term, you know what is the original intensity of the light source, you know the I depth color which is calculated here, the depth q color IDC lambda is also calculated here. In fact, it is a constant term which is set and put here. S naught is the term which is calculated from the lower expression based on the values of the range of depths and the range of scale values, which you are considering. Again, range of scale values will be always between 0 to 1. So, that is what you compute, and let us see how this functional form looks like. Okay. If you look at this particular plot, this is what we use to compute the S naught value scale factor. We need to compute this S naught here in this expression and substitute here on the top and calculate the computed intensity I lambda prime. So, you set your I lambda and IDC lambda which are known, original intensity of the light source and the depth queued intensity which could be different from the original intensity, and then based on your depth values and the depth which you are interested in of the object surface point. Z naught is the depth of the object point for which you are calculating the intensity. ZB, ZT, ST, SB are all set on this range. So, you set your ST and SB range of scale values which could be between 0 to 1. So, the minimum value of SB is 0, maximum value of SB is 1. Similarly, ZT, ZB also will have a maximum and minimum range. You can visualize again a normalized range from 0 to 1, since you are considering canonical view volume, it goes from -1 to +1 or 0 to 1, whatever be the normalized range, and that is what you send. So, Z naught will be some value between ZB and ZT as given here. This value of Z naught will be somewhere within this range, and if you see if Z naught is equal to ZB which is this point here, or even anything less than that, we assume that S naught is equal to SB. That is what we typically assume, that Z naught is equal to ZB. We know this term will be equal to 0. So, S naught is equal to SB. If Z naught is of course less than that, it will still remain SB, but if we are assuring or ensuring that the value of Z naught always lie between Z naught, between ZB and ZT. I repeat, Z naught which is the depth of the object point lies between the values ZB and ZT, that is minimum value of Z naught is ZB and minimum value of Z naught is ZT here, then, and it is a linear functional form. That means, when Z naught is equal to ZB, you have the value of scale as SB. When Z naught is equal to ZT, when that means you are reaching this point, Z naught is equal to ZT, these two terms cancel out and you have the value of S naught equal to this particular term. So, you can easily calculate that this is a linear function. As you vary Z naught from ZB to ZT, this value of scale runs linearly, goes up from SB to ST. Of course, you can have a nonlinear function of this variation. If you want, you can have a gradual exponential rise and exponential tapering at the end, typically like a sigmoid function in mathematics as it call about. Please read about that and see that you can fit a sigmoid function between for this value, which will result in a range of scale values for a certain range of Z naught between ZB and ZT. So, that is what you use here. Since we are assuming that the Z naught value will be lying between ZB and ZT, you will get a so for a certain value of Z naught, say here, you use this equation and get a value of scale S naught, substitute that in the front equation, and since I lambda and IDC lambda is known, you will get the value of I lambda prime. So, and minimum value of S naught could be 0. If that is so, what typically happens is this value of I lambda, in fact, when S naught is equal to 0, we will have the I lambda prime as your IDC lambda, and whereas when you have S naught is equal to 1, which is say the maximum value of ST is set to 1, and then S naught also becomes 1 when Z naught is equal to ZT, you will have the effect of that I lambda primes becomes equal to I lambda, because this term will be equal to 0. So, what you are saying is, as range varies from ZT to ZB to ZT, you are actually changing your illumination term based on the atmospheric attenuation or depth values, depth ranges from a minimum value of say IDC lambda to an I lambda, which is the source's original intensity. That means, when you are getting nearer to the object, you are almost getting your original intensity. As you keep drawing out, the I lambda term effect starts reducing and IDC lambda term starts increasing more and more. So, this is the range, and again we are only taking a simple linear variations from a very low value to a high value ZB to ZT. You can have a linear variation as shown in this case, but also you can have any nonlinear variation, but it could be should be a smooth, it should not be a jerky or abrupt variation. You can have a smooth sigmoidal function, making this variation of S versus Z vary in a sort of a smooth manner, like an S type of a function, sigmoid function as is talked about, is what you can use, and that is how the scale will vary with respect to depth, and in turn that will make the intensity also vary in a similar manner. Okay, so, those were the two terms which we have seen earlier, the effect of diffuse term and the ambient illumination, and the part which is left is the specular reflection. Okay. And we have seen these two terms. In fact, we talked about earlier there were three components of the illumination: the ambient term, the diffuse term, and the reflection, specular reflection. Okay. So, we have discussed at length about ambient term, we have discussed about in length about the Lambertian or diffuse reflection caused by the Lambertian surface, and you are left with the specular reflection. With the time available to us, we will introduce the specular reflection and discuss in details in the next class. With the time available to us, we will introduce the specular reflection component. As you can see here, it is an interesting phenomena of specular reflection is observed on a shiny surface, and we have now reintroduced this angle theta, which should be which is phi between the vectors v and n. We have the angle phi, we have the angle theta between n and s, and we have introduced a vector r, which is an angle theta between the vectors n and s. So, it is the same figure, the one more vector r introduced, which is bearing an angle theta between which is the same angle theta between n and s. The same angle theta is between r and n, and this r is called the reflection vector. This r is called the reflection vector, and the angle between v and n is the angle phi. So, now, this term which comes here, as you can see that earlier we had the vector n, then we had the vector s, and we had an angle theta between n and s. We also had the viewer direction vector v, and we had the angle phi between the viewer direction and the surface normal n. We introduce a vector r, which is with the same angle theta. Okay, the angle between vector r and n is given by the angle theta, which is the same angle between n and s, as if we can look back into the figure once again. And I must tell you here that the vectors r, n and s are on the same plane. The vectors now r, n and s are in the same plane, whereas the vector v can lie anywhere in 3D. This angle phi could be anywhere you should visualize again this vector in figure in 3D, where r, n and s are on this plane which you are seeing, let us say, and view vector v can be anywhere else in 3D. So, the plane which constitutes the r, n and s may not have the vector v, vector v could be somewhere else in this 3D. What is the significance of this r vector r which we introduce? It is called the reflection vector, because for a specular or a shiny surface, that is the vector which shows the direction about which the major or almost in some cases all of the light is reflected. Specularity of a surface or the specular reflection tries to model shiny surfaces. What are the examples of shiny surfaces which are different from ambient and totally different from diffuse? The most simple and the common example, given is a case of a mirror. In the case of a mirror, all of the light which falls on a mirrored surface gets reflected along in one particular direction given by this vector r, okay, given by this vector r. And in a case of a mirror, whatever light falls on the object surface will also get reflected along a particular direction. So, that is given by that vector r. If you assume a small tiny mirror patch, small tiny mirror surface patch, and it is illuminated by a ray of pencil, it is illuminated by a pencil beam, that is a single ray of light falling on that, then if the viewer direction is aligned with that vector r, then only you will be able to see the light reflected by that particular point. Okay. You can try this experiment small using a small patch which is a mirror type and allow the light ray to fall on that. You will not be able to see the reflected light from any arbitrary direction. In fact, on all directions except one particular direction, you will not be able to see the light reflected ray. Okay. And that particular direction is given by this vector r in the figure. If you see here, this is the vector r. If the viewer direction coincides with the r, or if you position yourself along the viewer reflected direction r, the vector direction r, you will be able to see the light source, single light ray which falls from the S and gets reflected by this r. So, we will stop with these words where we talk about that the shiny surface reflects light unequally in different directions, and mirror is an example of a perfect shiny surface. Other examples of shiny surfaces are, which are imperfect or non-mirrored type, are apple surface, shiny plastics, gold and silver coated metal surfaces, etc. I repeat again this paragraph which says that the shiny surface reflects light unequally in different directions. Mirror is an example of a perfect shiny surface. Other examples of shiny surface are imperfect non-mirror type, which surfaces are apple, surface of an apple, shiny plastics, gold and silver coated metal surfaces, etc. Now, comparison of specularity with diffuse. If you see, the diffuse surface or the lambation surface was reflecting light equally in all directions. When I use the word in an opposite way, that the specular surface will reflect light unequally in different directions. It may not actually reflect light in certain directions itself. Take the case of a mirror which is a perfect specular surface example. It in fact reflects light only in one particular direction and does not reflect light in all the other directions which is given by that vector r. So, along the r it reflects all of that light which it receives, and you know how to compute that. Given n and s and the angle theta, you will be able to compute r. We will see those expressions maybe in the next class. But here what we see here is that the mirror reflects light, all of the light in a certain direction which is given by this r, but there are other non-mirror type specular surfaces which are imperfect mirror type, like the surfaces of a gold and silver coated metal, let us say, shiny plastics, apple surfaces, clean apple surfaces. Okay. Clean, neat, the surfaces should be absolutely clean and neat and undisturbed, unperturbed. Those are cases where the light is reflected, major part of the light is reflected along r, that reflected direction, but some part is also reflected along other directions around that vector r. So, that is what we have to model. We will talk about, we will start from here in the next class, where we see how to model a mirror and other surfaces which are non-mirror but specular type. Non-mirror but specular type is what you have to model. And again I repeat, mirror is a perfect specular reflection case. Other non-mirror type specular reflections is what we have usually in practice available in front of us, and we have to model all of these. So, there is where we stop, and we start in the next lecture when we start from here onwards to discuss trying to model the last component of illumination, which is the specular reflection. Thank you very much.